Sounds good.
Hello, everyone. Today we have Sophia Marx from University of Massachusetts, who is going to talk about 2-Segal Simplicial sets and pseudomonoids in span.
Awesome. Thank you so much, Julie, for the introduction. All right. I'm very happy to be here. I hope my volume is okay. If anyone has questions at any point, obviously I can't see your faces when I'm sharing screen, but I'm very happy to answer them to the best of my ability. So interruptions are totally welcome, or I can answer more questions at the end. Yeah, so my current work, I'm a PhD candidate at UMass Amherst in the United States. This work is mostly expository. It's based on a paper called Frobenius and Commutative Pseudomonoids in the Bicategory of Spans by Ivan Contreras, who works at Amherst College, Rajan Mehta, who's one of my advisors, who works at Smith College, and Walker Stern, who's currently in a quantum computing mathematics group, I believe at Ankara. So this is part of a much larger program. It was a little tricky to motivate today's talk because it's understanding sort of Frobenius algebras and topological quantum field theories valued in categories of Lagrangian correspondences. This is a very, very small part of that, but the eventual aim and the sort of thing that excited me is that it uses some ideas from topology or ideas that are useful in topology to draw together, threads from classical mechanics, threads from symplectic geometry, from TFTs, and from higher category theory to sort of use these powerful tools all in the same place. There's the first sort of question that interested me when I was starting this research is why think about spans? Like, this isn't necessarily a category that people think about a lot. But this sort of Baez-Dolan groupoidification program from a few years back tries to understand linear algebra in terms of spans of groupoids. Spans sort of encode what it is for a morphism to maybe have some symmetric property. And it's this lens that you can also, on the physics side, which I'm not an authority on, you can sort of rigorously view these creation annihilation operators, look at Feynman diagrams, and sort of organize different kinds of combinatorial algebras in this way. This work also owes a lot to the sort of homotopy linear algebra perspective, which is in a paper by Galvez, Carrillo, Koch, and Tonks, as well as the Baez, Hoffnung, Walker works. And then finally, another thing that I'm very interested in is sort of understanding the world of closed two-dimensional topological field theories. So the cobordism category is very related to this as well. So hopefully that helps a little bit with what I'm coming in with here, which I'm aware is a sort of cryptic screen without explanation. So there's this idea that there's a bijection between two things that I will describe much more thoroughly. Isomorphism classes of 2-Segal simplicial sets, which are functors from the simplex category to, in this case, set. And then on the right side, we have equivalence categories of these things called pseudomonoids in span. And pseudomonoids are really just a categorically coherent idea of an associative algebra. So a long word to mean something that's probably pretty familiar. This bijection falls out as a corollary of an infinity categorical proof by Walker Stern from 2019. But the flavor of that proof involves a lot of mathematics that, for me, as mostly a topologist, was pretty unreachable. So one of the big motivations of this paper is that it sort of reintroduces all of these ideas and the correspondence in terms of a graphical calculus that's much easier to sort of get your hands on and manipulate. So I'm going to be focusing a lot today on not really talking about the infinity categorical side, although there's a lot of motivation there. I'm going to focus instead on this graphical calculus that I think we can sort of get our hands on and get dirty with more easily. The main contribution of the most recent paper, just for the sake of research, has been to extend this correspondence to if you have a simplicial set with some additional structure. So if you have something called a paracyclic structure on the left-hand side, you get a Frobenius pseudomonoid on the right. We like Frobenius algebras because they're these sort of simultaneous algebra coalgebra structures. And are very related to topological quantum field theories. And then if you have a gamma structure, whatever that is, on the left-hand side, you get a commutative pseudomonoid on the right, clearly a very desirable property. So yeah, so let's get into talking about what these things actually are. So first, to meet the category, so span is a symmetric monoidal bicategory. If you haven't worked that much with categories or monoidal categories, it doesn't matter too much. The monoidal just means that there's sort of a notion of a multiplication in the category. And in this case, it's really just, sorry, I am left-handed, so I will block the camera every time I write, but we're just gonna roll with that. This is just the Cartesian product. So familiar. And the objects in this category are just sets. So super familiar. One morphisms are spans of sets, which is this triple of sets plus two set maps, mapping down from the sort of apex of the span. Again, the sort of motivation for spans is that they encode the idea of sort of like, what if a morphism had some sort of symmetry property? Like you can see that if F1 was the identity map, you'd get a morphism one way, and if F2 was the identity map, you'd get a morphism that went the other way. And then two morphisms are if you have two spans that have the same source and target. So we read this as a morphism from X to Y. Then we have a map A to B. And the easiest way of understanding this is sort of saying, what if this diagram commutes? So if we go A from X to Y, and we have B going up this way, no reason we can't turn it upside down. We have some map H here such that that diagram commutes. And then for the sake of the monoidal structure, our identity is just a triple of objects with these two identity maps. Composition of one morphisms is given by the pullback, or some of you might have seen this as a fiber product. So if we have two spans, we can sort of stack them horizontally in this way and take the pullback above to take their composition. That's sort of the basic idea of how span works. I won't go into all of the bicategorical coherence conditions and the other bicategory maps here, but MLab's a great resource if you want to go into the full Monty on that. So what does it mean to have a pseudomonoid in span? So as I've said, this is sort of like a coherent version of an associative algebra. So in general, if we have any monoidal bicategory C, we can make a pseudomonoid in this category by taking a distinguished object in our category. So that's going to be the input to all of the things that we do in our algebra. So you could imagine having a vector space V if you want something to work with in your head. So we have this distinguished object X. We have a one morphism eta, which is the unit. So I here is designating the neutral object for the monoidal operation. We have a one morphism mu, which is our multiplication. So it takes two inputs and outputs one thing. And then we have these three invertible two morphisms. We have an associator, which connects multiple bracketings of an n-fold product. So if you have, A, B, C, goes to A, B, C. And then we have left and right uniters that cancel out the unit on the left and right. So these definitions are fine, but my favorite way of looking at these is through these sort of string diagrams that we'll introduce momentarily. All this data to work out has to satisfy these two coherence conditions, the triangle equation and the pentagon equation, maybe familiar to some of you, that I'll show in a second. And to think about these more easily, we can use this sort of graphical calculus of string diagrams. So those of you who have seen, the cobordism category before and things like that will be very familiar with the idea of these. They really do look like cobordisms without the sort of wiggly tube property, just thinned out. So we can represent eta as this little bubble with a string coming out of it, just because it's hard to otherwise differentiate the ends of things, where our multiplication looks like this classic tree structure. We can also use this graphical calculus to represent two morphisms, right? We can take maps of these. So for example, I think this is the nice intuitive version of looking at what the associator does. You have three things here, a triple product, and you can either multiply first with another single input and then multiply again this way, or you can multiply first on the right side and then multiply again there. So we're looking at composition as being a vertical process and the monoidal product as being sort of horizontally indicated. This is also showing what the left and right uniters do, right? You're sort of saying that topologically speaking, you can basically retract the unit into something that then straightens out to become an identity in either direction. So here we're retracting the unit on this side and getting an identity morphism. So hopefully that makes all of those things make a little bit of intuitive sense. Then just for rigor, here's what the triangle equation and the pentagon equation look like. So it says if you do A and then L, this is the same thing as doing R, and, vice versa. And then the pentagon equation for the associator. Okay, so what if we have extra structures? So if this seems a little unmotivated, it's not going to be super used later on, but I think it's useful to just see what our commutative and Frobenius pseudomonoids look like. So this is all of the above. Data plus we get an extra invertible 2 morphism. Which satisfies this property. So if we do, let's call this gamma. So if we do gamma, we get this. And then we do gamma again to get this sort of double twisted picture. This is the same thing as if we did this map, which I haven't actually described to you, but if you're interested, this is the solipsis map. This comes from the bicategorical data. So that's just some coherence condition to get this sort of twisting of the multiplication, which makes sense for commutativity. And then Frobenius pseudomonoid, well, Frobenius means we have sort of simultaneous coherent algebra and coalgebra structures. So what that translates into in string diagrams means we should have some concept of sort of turning things upside down. So we also get the above stuff plus a co-unit, which is just an upside down unit, which we'll call epsilon, going from x to I, such that this pairing, if we take co-unit composed with the multiplication, I'll show you what this looks like momentarily, is biexact. And what we mean by biexact is just that there's also a co-pairing. Again, turning everything upside down, which I think I'll call beta. So I to x times x. Throughout this, I'm routinely going to use the tensor product as just the generic monoidal product, such that, oops, sorry. And then we need two morphisms to go with that. So C and N, invertible 2 morphisms, such that, I need more space. So if we represent epsilon by this string into this little bulb, alpha is this sort of co-multiplicative or multiplicative looking structure, but we can, again, as with the unit, we can sort of collapse in the co-unit to become this sort of little U-bend turnaround. And then beta similarly is this sort of turnaround in the other direction. So you can think of this as sort of like a binary operation with no output, or like the co-version of that. And then Z then turns this into the identity and N turns this guy into the identity. So the idea here is that basically you're taking something where if you studied Frobenius algebras, you sort of get the full snake lemma applying. Yeah, we won't really return to that, but I think it's a useful extension. So, all right, so to ground this, so for the left-hand side of our equivalence, we're saying that 2-Segal simplicial sets are the objects that we care about. So yeah, so we should probably have some notion of what is a simplicial set. So some of you might have seen this before, but I hadn't before I started this work, so I'm gonna give a brief introduction. So the simplex category which we generally denote delta, has as objects the set n, which here means 0, 1 through n. And as morphisms, these are order preserving or weakly increasing maps of sets. So, you know, in the naive little diagram, it's a map such that arrows don't cross, with no other restrictions. And then the morphisms, yeah, we got. So a simplicial set, it comes from the fact that delta has this sort of natural set of generating morphisms. Morphisms, which are, so these sort of maps that map down. So these are maps that skip our element I in the set. So these are the injections, which we call coface maps. And we have the maps that send two elements to I, so the surjections. Which are the codegeneracy maps. So if you think about it for a minute, you can sort of convince yourself that these will generate all of the weakly order preserving maps that we need. So a simplicial set then is a collection of sets so it's a functor from, so a simplicial set is a functor, which I like to call x dot standardly. This is a contravariant functor to set. You could also more generally consider simplicial objects in most categories. It's just an issue of, you know, set is the easiest thing to work with here as a target. So the way to think of a simplicial set is as this collection of sets xn for all the integers with maps that are dual to those coface and codegeneracy maps. So we have face maps that map down a dimension and degeneracy maps that map up a dimension. And they follow these relations called the simplicial relations, which we won't use much here. The best way I think of visualizing a simplicial set, which is, a generalization of a simplicial complex, is that we have sort of a set of points in 0, a set of edges in degree 1, a set of faces, triangular faces in degree 2, then tetrahedra, etc. And these sort of quivers of maps between them. We like simplicial sets in topology because they're sort of an easy combinatorial model on which to do homotopy theory for topological spaces. For those of you who are interested in that thing, so there's the total singular complex functor, which goes from top to simplicial set, and the geometric realization functor, which goes backwards from simplicial set to top, and that's an adjoint pair, so you can sort of always get one from the other. Yeah, so that's a simplicial set. So the base objects we're working with are simplicial sets, and we'd like these simplicial sets to all be 2-Segal. So let's talk about what that means. So a 2-Segal simplicial set is, so you have a simplicial set, so given a simplicial set x dot, let's make it 2-Segal. So we have, from the simplicial structure, a sequence of sets, x0, x1, 2, etc., all the way, and base maps din, which map down, and degeneracy maps, which we call S, that map up. So the first step is to do this in the graphical calculus is to identify our xn with the regular n plus 1 gone. And then we can consider this map that comes from triangulation. So consider the map hat induced by any triangulation. And this map goes from xn, our regular n plus 1 gone, to this fiber product of x2s. Fibered over x1, where there are n factors on this side. And how this map works, so since each triangle in our triangulation T is given by its vertices, so vertices labeled such that there's an ordering, so V0 less than V1 less than V2. We get an induced map, which goes opposite, so from 2 into n. So this is 0, 1, 2. This is 0, 1, n. Which gives, by our simplicial set, so yielding a map that goes from xn to x2. So each factor of this fibered map is each possible map from 2 injecting into n. So each of these is one component of T hat. Each of these possible maps is one T hat. And so to understand what this actually looks like, so if we triangulate the square, okay, so remember we can identify x3 with the square, the foregone, and we have two possible triangulations of the square. So our vertices are labeled, and we can now describe these two induced maps that we get from the two triangulations. So, and it turns out we can describe these induced maps in terms of the face maps of our simplicial set. So for T13, the left-hand triangulation, we're going from x3 to these, the sort of product of these two triangles, where the condition of the fiber product is just the same thing as saying, okay, two triangles agree on an edge. You can sort of imagine that's the shared image there. So this map says, okay, so we have a psi in x3 identified with this square, and that then maps to D3 of psi, where D3 means you delete the triangle with apex 3, and D1 of psi means you delete the triangle with apex 1. So psi is mapping to D3 of psi, D1 of psi. And the same thing on the other side, so T02 is doing the same thing, but here we're deleting this triangle and then deleting this triangle. So the idea of being 2-Segal means that a simplicial set is 2-Segal if for any triangulation of the simplicial set, this map T hat is an isomorphism. So we have an isomorphism between x3 and the triangulations, no matter which way we triangulate. So the idea of being 2-Segal here is being presented very geometrically. In fact, the way we're using it is to encode some kind of notion of weak associativity. The idea of 1-Segal, which is sort of the original Segal condition, encodes a strict associativity. So that's a fiber product one dimension down. So x1's fibered over x0's on the right-hand side. And I think I'm going to be able to illuminate better why this is using an example. So, okay, so groups are friendly. So if we have a discrete group G, and we want to say that we're going to construct the nerve of our group G. So various nerve constructions are just sort of like a rich mine of examples of things that are either 1-Segal, 2-Segal, or both. So what this means is, so this, we read this as the nerve of G. I apologize if people have seen this before, but hopefully you haven't. So this means that, so for each n, xn is just a tuple of n composable or multipliable elements of G. G, I, and G. And what are our face and degeneracy maps? So DIN means multiply GI with GI plus 1. And the degeneracy maps, SIN, mean insert an identity element at index I. And then we can describe, so now, so we can describe the maps, isomorphisms, T hat. So G13 goes from this triple product to this image, 3, G1, G2, and the other one goes again from this triple product to, here the image under D is G2, G1, G2, G3. So what the upshot of this really is that we can think of, so T13 corresponds to this bracketing of the triple product. And T02 corresponds to this other bracketing of the triple product. So hopefully this model helps us see a little more clearly that X3 in this case, so looking one dimension up, is playing the role of an associator. So it's mapping between these two possible rebracketings of the triple product G1, G2, G3 in our group. We can generalize this idea to higher n+1 GONs, which means we can correspond we can go between multiple bracketings of, say, an n-fold product. It doesn't have to be just a binary operation. One nice consequence of a simplicial set being 2-Segal is that all higher dimensional simplices can be drawn planarly. So we can always draw them. It's this property of being sort of 3 co-skeletal. So all the information is encoded in a planar diagram as a polygon with potentially some subdivisions. So this means that we can use our graphical calculus in this context as well. So just as an example, this is saying, okay, we have something in X3, that's the square. These C's are elements of X2 triangles. We can take the face map G31 to map down to X2, which just deletes C, and up to some relabeling of vertices, we've now produced an element of X2. And this works for higher dimensional simplices as well. You could imagine pentagons, hexagons, etc. Okay, so now the sort of meat of the argument, like how do we get a pseudomonoid, so the right-hand thing in our equivalence, from a 2-Segal set, the left-hand thing. So just as a note, here we can generalize from triangulations to consider any kind of subdivision. We know that a triangulation is always admitted. So the first step is to consider the dual graph of some subdivided n+1 GON that we're associating to xn. So this gives us something called a labeled rooted tree, labeled just because we can label. So the system is, right, we're just labeling by the highest vertex on each edge. So remembering the edges are elements of x1 here. So we get this tree from our subdivided n+1 GON. Rooted trees also are really nice mathematically. They form a Hopf algebra, and you can do a lot of things with them in general, but we're not going to use a ton of those properties today. So we can associate a span to this tree, right? This is already looking a little like our morphism calculus from before. So for example, here in the top layer, we've got 3 copies of x1, and remember the tensor product or the monoidal product is interpreted horizontally. So this is x1, tensor x1, tensor x1. The apex of our span, which I've drawn, vertically this time, is this fiber product of x2. So that's the entire subdivided square, and then the root at the bottom is a single x1. So you can imagine this being sort of like a triplicate version of a multiplication. More generally, we can assign this span that has x1 to the n for these sort of top leaves going through the sort of middle zone, which is this polygon xn, and having a singular output for the root. This can be any n+1 valent vertex, so we can get any kind of n-fold multiplication, which then in particular allows us to derive this mu, which is the multiplication one morphism in span. So this is our first piece of data for getting our pseudomonoid. And then to get our associator, we can consider this diagram, which is taken from these 2 triangulations of the square. So we have these isomorphisms that come from the 2-Segal condition, t-hat13 and t-hat02, which if we take the dual graphs of each of these, we get this triple of rooted trees, which are all isomorphic. So we can construct this associator by, we have an isomorphism, we can invert by just composing both, right? Because this is connecting the version where you multiply 1 and 2 first, and then multiply in 3 with the 1 and then 2 and 3 multiplied. And if you write out all the diagrams, you can kind of quick check that it satisfies the pentagon equation, just a bunch of figures. And if you want to see that, it is in the paper that I referenced at the beginning of the talk. For the left and right uniter two morphisms, so there's this canonical identification of mu composed with eta cross 1. So if it comes from the face and degeneracy maps. So this guy is fibered over S0 D2, and it sort of takes something from being in the image of D0 to being in the image of D1. This is a map of spans, right? That is then, so a two morphism, going to take us from the identity on X to this guy, which is going to let us build something that satisfies the triangle equation. That's what we're hoping for. So the condition of X dot being 2-Segal again saves us here. So this map is an isomorphism, which means we can invert it and get the left uniter. The right uniter is similar. And so to show this all pictorially, so here we've got the same idea plus one new map S. So that's coming from the span above. And all of these maps are isomorphisms under the 2-Segal condition. So if we consider that this picture is related to that span, I just redrew it, then we get an isomorphism between mu, which was again our multiplication to this span here, which I call A. The upshot of all of this is that, and it might have been helpful if I put a couple more pictures in, we have a way to rewrite all three of our two morphisms in terms of these isomorphisms, which means we can just compose to get the triangle equation, which just says that R is the same thing as L composed with A. So we have a multiplication, we have a unit, and we have left and right uniters. I'm not going to be able to go fully into the opposite way. So how can we get a 2-Segal simplicial set from a pseudomonoid? But I can at least sort of like gesture at it. So if we have, so given a pseudomonoid in span, so we have a distinguished object which we can call Y1. This is sort of suggestive notation because we know it's becoming a simplicial set. The unit eta, which goes Y0 point, and then this map here, Y1, the multiplication mu. So we're going Y2, and this is Y1 cross Y1, this guy down to Y1. We can self-compose mu iteratively to get an n-fold multiplication. Yn, here's Y1 to the n, and this is Y1. So this really is all we need to get a simplicial set. So this process yields a simplicial set, Y dot, where, so what are the face and degeneracy maps? So the degeneracy maps that are S, R, N, come from composition with the unit. The unit eta. So we have R naught 2. R naught is eta. This guy is 1 constant 1. 2. Here's our multiplication. Y1, so that is sort of the how you can build up in dimension. And the face maps, yn, come from just restrictions. So restrictions to subproducts of product in n-fold multiplication. With the caveat that sometimes we need to use the associator here. Sometimes the associator A. Y dot is then automatically 2-Segal because you can sort of see from by construction the n-fold multiplication yn is just built up of y2 factors fibred over y1. So we get the 2-Segal maps from that. And yeah, that's a slightly rushed version with fewer pictures, but that's the general idea of how you get one from there. There are a lot of examples of 2-Segal sets out there. The nerve of any small category is 2-Segal. We saw how the nerve of a group is 2-Segal. The nerve of a partial monoid is also 2-Segal. And there are these things called effect algebras, which minus a certain extra stipulation are also 2-Segal. These are kind of interest because they work as a model of like fuzzy logic and quantum computing. And then of course 2-Cob. So the cobordism category is under some genus constraints is 2-Segal, and there's I can help with references to papers about that if you want to know more. Yeah, I think that's actually all I'm gonna go into today. Thank you all for your attention, and yeah, let me know if you have any questions. I'll stop the share.
Thank you very much. Good talk. Gonna stop the recording.